Hello, my friends. Today we're going to be talking about work and power. The first thing we're doing is understanding what work is, and then we'll understand what power is, and we'll actually learn how work. There's two ways to think of work, and we'll learn kind of both ways today. Awesome. So today we're going to talk about understanding work. When we think of work, we oftentimes think of getting paid, a job, doing some stuff, being tired. And those are all great ways to think of work. And in physics, we actually have a very specific way we define work. And work, simply put, is the amount of energy required to move an object. And when you're thinking about it, that's what work really is in like a job work, right? So you move things around. You might be typing on a keyboard doing an office type job, but you're pushing the keys and moving them around. You might be writing with a pencil. Again, you're pushing something around, moving it around. Heck, you might be picking up a 2x4 and carrying it somewhere else. Then you're doing work as well. So all these things that we think of as jobs require tons of work, and work is just everywhere around us. Even when we don't think it's around us, it's always around us. And so this is one of the first definitions. So it's the amount of energy required to move an object. Well, that means that there's two things going on with work. First of all, to move an object, you have to push on it. So the amount of pushing makes a difference. Because if you push harder, you're going to be doing more work. You're going to be more tired at the end of the day, the harder you have to push. So for example, pushing your backpack across the room is a pretty easy thing to do. Pushing a desk or say a couch across the room, it takes much more force and you get more tired afterwards. You'll wear out much faster that way. And the other thing you have to do is you have to actually move the object. So how far you push the object is going to be the other key point in work. The farther you have to push, the more work it is, and that just makes sense. If you push the couch from against the wall to the middle of the room, that's not as much work as if you have to push it all the way down the hall, into the basement, down through the stairs, all that stuff. Okay, now in the equation we're going to find out that how hard you push the object. Of course, we call that, I'm going to change the pen color real quick. We call that the force acting on it. And of course, how far you push, we call that a distance or a displacement. Typically, we call that distance here. And the equation simply then is the work you do is the force you apply, and that's the net force, times the distance you push. So force times distance. Now, technically speaking, and this force has to be parallel to the direction. So it's the force that's in the direction of the motion. So if somebody else is pushing down on it, it's not doing the work when you're pushing forward. But we won't have to worry about that in this class. So let's do just a quick thing. So let's say that we have a box here, and it's sitting on the floor, and we're pushing it forward, and we have to push it to get it to move across the floor because there's some friction backwards. And let's say that we're pushing with 25 newtons, and we push this box from here to, and assume this is a straight flat floor. I didn't do a very good job of it, although it really doesn't matter. It doesn't have to be straight or flat. And I push it to here something later, and this distance between the two is 5 meters. So the question is, well, to do that, I'm obviously going to get more tired from doing that. I'm going to lose some energy, and the energy is going to be the work done. So let's plug this in. The work is equal to the net force, right? So we have 25 newtons. Oh, that's just straight wrong. That should not be net force. I apologize. I got carried away. This is the force you apply. Let me make that really explicit. This is the force you apply because we're looking for the force or the work that you're doing, and this is the distance you push. So here, the key here is the you part. I should never have put the net on there. I apologize for that. So this is how hard I'm pushing on here, and this is the distance traveled. So I'm pushing with a force of 25 newtons. And the distance between the two is simply 5 meters. And we do this math, we find that, hey, the work is equal to 125 Newton meter. So Newton times meter is a Newton meter, and that's a really weird unit. We have a special name for this unit, and it's called a joule. So this is equal to 125 joule, and joules are the unit of energy, of all types of energy are joules in the metric system. And a joule is really an abbreviation, and the real units are kilogram meter squared per second per second. And this is just a big jumble to say, so we have this abbreviated joule thing going on. All right, so that's it for that part of work. Let's see if we can do a comprehension check. So on this one, what I want you to do is rank the description below from least amount of work to the most amount of work. And they're the 4 things you're going to rank. Go ahead and pause the video, give yourself a few minutes, look at each one, think about which one that you want to put as least and which one most, and then fill the middle ones in as well. Go ahead and pause the video now. All right, awesome, you're back. Let's do this thing. So the way I like to do these, I like to go from least to most. Do the extremes first. So when I look through here, lifting a heavy box above your head. Okay, that's going to take some work. Lifting a light box above your head. Okay, so that's going to take probably less work than the heavy box because the heavy box is going to require more force. So this guy's more than that one. Trying to lift a box that is too heavy for you to lift. So here, you're really pulling really hard on the box and you're not making it move. And because here, the distance is equal to 0 meters, 0 meters times any force means you're not doing any work. So you're not actually moving it at all. This is a 0 work one. So this is the lowest for now. So this looks like this is going to be the first one. And then holding the heavy box directly in front of you for 2 minutes. Wow, I would sure get tired if I did that. But notice, here again, we didn't actually move it. We're just holding it. Now to get it from the floor to out in front of you, you did some work. But once you're holding it still for these 2 minutes, your distance is 0 meters, your work is 0. So on this one, we're going to go least. And the first thing is a tie. 3 and 4 go here. These are tied. And then this is most here. And the most is number 1, lifting the heavy box above your head. Lifting a light box above your head. That's number 2. And I could have put another one here of lifting a heavy box like halfway up to your waist. And that would have been somewhere in the middle. Sound good so far? And now notice that these 2 guys, work is equal to 0 in this one because we have 0 distance moved. Now here's the problem though, is that I hate this because 3 and 4, both of these you get really tired. So if you were to stand there and just try over and over and over again, just constantly trying to lift a box but didn't, you would get super duper tired. And that seems to imply that, hey, there's some work going on. And there is. It's just not on the box because the box isn't moving. Let's take a look at that real quick. When your muscle fires, so let's say we're holding the box right out in front of us. When your muscle contracts, the muscle doesn't contract and then lock in place. Actually, those individual muscle fibers, some of them are contracting, and then they can't stay contracted, so as they relax, other muscle fibers kick in and contract. So you have this constant back and forth in your muscles going on with some contracting and making up for each other. So you get this really cool process of things constantly moving. So inside that muscle, in here, when you're doing stuff, there's going to be some contraction and some releasing in there all the time. So there's constant motion inside that muscle. And then that's what leads to there being work being done in the muscle on all those fibers, but not on the object because the object's not moving. Now, not everything works that way. I got a video here for you. Not all muscle, I should say, work that way. I've got a video here of our good friend, the starfish. So this video is of these sea stars, and they're going to go eat a mussel.
Like an advancing army, the sea stars move into position, slowly but surely working their way up toward their victims.
This is creepy time elapse. That's why it's happening so fast. They're really, really slow.
The mussels cannot run or fight. All they can do is hide within their shells as their killers crawl over their bodies. Sensory tube feet sweep over the tightly packed mass of shells, searching for any gap in the muscle's defenses.
Now, what happens is this sea star that you're seeing on the screen here, it's going to hover over a mussel or a clam, and it's going to have to rip that thing open so they can eat it. And to do that, you'd think, wow, that would take a lot of work because they just sit there and just constantly pull and pull and pull. But what they do instead, though, is they have this really cool feature where they grab on with their little suction cups. They grab onto the mussel and they just pull on it as hard as they can. And then they have this cool feature where there's connective tissue in them that can harden. So instead of having to keep pulling and pulling and pulling with their muscles, firing over and over again, they pull and then they harden up and they freeze in place, freezing that tension. And once they've done that, their muscles can relax and they can just sit here and they're just sitting there pulling on it without having to use their muscles. So they're not using energy like you would be trying to open that clam. And then as that clam gets tired and releases a little bit, they soften that tissue and they become flexible again and they pull again. And they harden up and they sit there and they hold it and they have that tension. So it ends up being able to not do any work but open up this clam slowly over time. And then afterwards, it actually spits out its stomach into the clam.
Its victim, the sea star hunkers down and begins its attack. The miniature camera, tucked within the mussel's shell, gives us the first look ever at the carnage that unfolds here every day. Once the tube feet have physically breached the mussel's defensive line, the sea star's translucent stomach begins the final assault. The animal actually pushes its stomach inside the mussel's shell, unfolding like a fatal flower.
So when the sea star does this, it would be like you reaching into your mouth, down your throat, grabbing the bottom of your stomach, and then pulling it all the way out. And when it does that, it actually inverts the stomach so that the inside is sticking out. And all that juices and stomach acid and all that nasty stuff in your stomach would just right out onto whatever object you put your stomach on. It would sit there and dissolve it. And then when you were ready, you would just just stuff your stomach back in with all that dissolved goo stuff on it. That's delicious, delicious food. And that's what the sea star does.
The stomach unleashes a volley of chemical weapons, digestive juices that dissolve the muscle's soft pink flesh. All that's left is a nutrient-rich soup, a broth that's quickly absorbed by the sea star. Having assimilated the muscle, the sea star's stomach pulls away, and the animal moves on, leaving behind an empty shell.
All right, so the purpose there is when you hold something still, your muscles are doing constant work by contracting and relaxing. But they're not doing work on the object you're holding. They're doing work internally inside your muscle. Whereas a sea star is really cool because they can do work, they can pull really hard, and then they can freeze and hold that tension without doing any more pulling. They just sit there with that tension on. And that's how they're able to overcome a clam. There's a second way to interpret work. And what happens is anytime an object gains or loses energy, the way it loses or gains energy is there's either work being done on it or work being done by it. So when I do work, I lose energy, and something else gains that energy, and the object I'm doing work on gains that energy. Right? And that happens anytime there is a change in energy or a transfer of energy. All energy is transferred by work. So that means that anytime there's a change in energy in a system, so something changes energy, that there was work being either done on it or done by it, and the amount of change is equal to the work. So we can actually write work as equal to the change in energy. Now you don't need this equation, so there's no reason to write this down other than it's interesting equation. We'll come back to it in the future just to say, hey, anytime there's an energy change, some work was being done, and we'll connect that up as we go along. Now let's get on to power. So understanding power, let's start talking about that by figuring out which of these two would take the most work. Pushing a heavy box across the room quickly or pushing the same heavy box slowly. Now, at first glance, you might say, "Oh, pushing it quickly, man, that would be way more work." But if we look at the equation, work is equal to force times distance. Work is equal to force times distance. It would take the same force, right, to push it at constant, steady speed fast as it would slowly. So the forces are the same, distances are the same. The work actually ends up being exactly the same. So here, the works are equal, even though one was done quickly and one was done slowly. So the amount of work is independent of the time it takes to do the work. So if you do something slowly or do it fast, it's the same total energy either way. However, power, when we're talking about how fast something's happening, how fast work is being done, what we're really talking about is this new concept of power, right? And power is how quickly you're doing work, so how quickly energy is being converted. And the equation is actually pretty straightforward. And if it's a rate of something, it's going to be per time. So power is equal to the amount of work you do divided by the time it takes you to do that work. Okay? So now power isn't an energy, it's a rate of energy conversion. Subtle difference there. So let's say that you do, here, again we have that nice box, it's a nice and exciting example, and you push that box some distance, let's say we're going 3 meters this time, and in order to push the box you have to push with 100 newtons of force. And we have a stopwatch and we say, okay, so let's time that. It takes you through, I don't know, let's say 4 seconds to get there. So 4 seconds from here to here, that's the time elapsed that happened. So to find it, all we do is find the work. And of course, the work is equal to the force times the distance. And we divide the work up here by the time. So we say, okay, so force times distance, force is 100 newtons, times the distance of 3 meters. And then we divide that by how long that took, 4 seconds. And our power ends up being 300 divided by 4, 75. And here we have a Newton meter, again, is a joule. And so that ends up being joules per second. And we have a special word for joules per second, and we call those watts. So it ends up being 75 watts. Now, so what does this 75 watts number mean? It means when you move this box from here to here, pushing with 100 newtons for 3 meters, you did 75 joules of work every second in order to get there in 4 seconds. Okay? So this is the rate at which you're using energy. You're using energy at 75 joules per second, or 75 watts. All right? So far, so good. So work is the amount of energy. Power is how fast it's being converted, or how fast it's being used. Let's move on. So on these guys, I want you to rank them from least to most power. Okay. And be careful here because there's 2 of them are tied. You have to find some. There's 2 of them that are tied. So in the end, you're going to have least, and there's only going to be 3 lines, and most. And there's going to be 2 of these numbers are going to be on a single line with each other tied. Okay, pause the video, give yourself some time to check this out, and hit play when you're ready. Okay, here we go. So pushing a desk halfway across the room in 10 seconds. So we're pushing a desk halfway, so this is not very far, so a fairly small amount of work here. and it took us 10 seconds. Okay? So pushing a desk halfway across the room in 5 seconds. We're doing the same work because we're pushing the same desk the same distance. So it's going to go across the room in 5 seconds. So we're doing it faster. So in less time means there's going to be more power. So this one's going to be more power than this one because it's done in less time. And then pushing the desk across the room in 10 seconds. So instead of halfway, we're going all the way across the room. So this is more work in a lot of time. And this one is pushing across the room, more work in less time. This is going to be the biggest one because you have the biggest work in the shortest time. That's the most, 4. And let's try to find the least one. So the least one was the smaller amount of work in a whole bunch of time. It's going to be less power because we're going to be doing using less energy every second. So over here is going to be number 1. And the tie then goes to these two guys. Here, we're doing half as much work, but in only 5 seconds. Here, we're doing twice as much work in twice as much time. So we're going to have the same power output. We're going to have to use as many joules per second to do twice as much work in twice the time. So 2 and 3 go together. So we're trying to figure out how much work and power it took to move a 50 newton, not took, I shouldn't say that. So what your power output was when you were pushing with 50 newtons on a box that weighs 350 newtons, a distance of 30 meters, 25 seconds. So let's take a look. I'm going to draw a quick force diagram. We've got a box here. And we're pushing with 50 newtons. We're pushing this way with 50 newtons. And it weighs 350 newtons. So this one's this way, 350 newtons. And we're pushing it over to here, this new location. And this is 30 meters away. And we're going to do all of this in 25 seconds. So I've got all my stuff figured in now. Now, when I'm trying to figure out the work and power output for me, I look at this and I say, okay, wait a second. This is the force for me. That's the force I want. I don't care about this force. And remember, we also said that the force has to be parallel to the movement of the object. And this is the force that's parallel to it straight across here. So I'm going to ignore this 350 Newton garbage. I don't want the weight. I want how hard I pushed. So here, my work is equal to force times distance, which is equal to 50 newtons times 30 meters. And that, of course, is equal to 1,500 Newton meters, which we call joules. So there's my work. And then my power is going to be the work divided by the time. And I'm going to put here, I'm going to say, okay, my work was 1,500 joules. And my time was 25 seconds. And when I divide that, I get 60 joules per second. So in order to accomplish this in 25 seconds, I'm going to have to put out 60 joules of energy every single second. And of course, we call that 60 watts. That's my power output. That's my energy used. Awesome. So that does it for work and power calculations. We'll pick up here in class.